Alright, so let's start discussing the rigid body problem, or if I may use the word, the simplified rigid body problem and of translation plus rotation. So we have now a clear idea of the problem that we are solving. We want to predict the motion of translation plus rotation and of a rigid body, and that means the following. Number one, I need to tell you the position of the center of mass, and which I'm just calling it as xcm and ycm as a function of time, and this is just the motion of a single particle, the center of mass. Now it's important for you to realize that we are doing the simplified version where the object is moving in the xy plane. Now for this simplified problem, the following needs a little bit of imagination, not too much I would think. You have to imagine yourself as a traveler moving along with the center of mass, and if you can see through the eyes of this particular traveler who is moving along with the center of mass, then what he sees from the object is just a change in the orientation. So this angle theta as a function, theta changes with time. So this is the orientation of the object with respect to this traveling axis, x-axis, theta as a function of time. So can I predict, in addition to the center of mass, theta as a function of time? And now this is our problem, and this is called the rigid body problem. So last time I said there'll be two types of problems, and one of them was the rigid body problem. Now before I give you the details of the problem and how the solution comes about, let me tell you the answer up front. This is part 1 and this is part 2. Part 1 is called translation, and part 2 here is called pure rotation. Now part 1 is something that you already know. This is the main thing. Part 1 simply comes about with the help of a equation which is looks exactly the same for particle mechanics, which we've been learning so far. So F external on the system is equal to the mass of the rigid body into the acceleration of the center of mass, and this is enough for particle mechanics to tell xcm as a function of time and ycm as a function of time, given the initial position xcm at 0 time and ycm at 0 time. There you go. Part 1 is solved, right? And where does this come from? It comes from an equation that we are very happy with, F external system, law that we find it very acceptable, is equal to this is the first Newton's laws. And now what about this part of the problem? So I'm going to give you the answer now. This is going to be predicted by an equation. It's getting a little clumsy here, so maybe I'll just erase this part and write down the answer for the second part of the problem. So now whatever I'm going to write has to be justified, and that is the content of this video. But let me tell you that the answer itself is very easy. So the second part of the problem comes from an equation which looks, for this simplified problem, which can be written very nicely in the form of a scalar equation, tau cm about the z-axis, the moving z-axis at that instant, will always be equal to ICM, which you can find out from any of the tabulated handbooks, into alpha, which is the alpha as it is to this observer, and this, according to Charles' theorem, gives us um, any possible translation plus rotation. Right. So this equation is enough to tell us theta t as a function of time, given again the initial condition theta 0. Right. So here we see that this is the big question mark. Where did this come from? Okay. So now we shall proceed to discuss this equation. But the take-home message is we've solved the first part of the problem and the second part of the problem with relatively simple equations which we can handle. Right. So let's get back to this main part of the story. So I gave you the solution, and maybe it is worth writing it neatly one more time. The solution is, the problem is, okay, let me write down the problem. The problem is, what is XCM, what is YCM, what is theta, and I want you to make sure that, please imagine yourself as the observer when you think of theta. What are these three quantities? And the answer is, this part, which I'm calling as translation, is related to this equation, which I hope is one of the friendlier equations that you will ever come across, and which you already seen. It's exactly like the particle mechanics equation, so the problem is solved. This one has its solution coming from an equation which looks so nice. Tau z scalar for the simplified problem, ICM alpha t. Okay, so done. So this is part 1, part 2 done. So now I shall justify. I don't need to justify this. This is acceptable. I need to justify this. Okay, I'm going to justify this, and this is going to take some time, and at the same time this will clear up many basic ideas that you need to know in this chapter. Very interesting ideas, I would say. Right. So here is our law, and we've written this down so many times that you clearly realize that it has been done on purpose. I just want to highlight the fact that this is a law of nature, and which has been well verified, and this is all we need for the problems of translation plus rotation. But like I said, we are solving a simpler problem, so maybe we should just write it like this. Okay, so please note that we are focusing on this because it's a little simpler, and well, I'll tell you why this problem is much simpler than this. I'll tell you at the end of the whole story why this is much simpler than this one, but let's stick to this because there are many interesting problems. Right, so this is the law, and how do I use this? How do I use this to do what? Of course, the topic is translation plus rotation problem. Okay, so I'll tell you, it's pure common sense. First, we need to ask ourselves a question. Can I find out tau? Okay. Is it possible for me to find out tau? Next, can I find out LZ? Oops, it's worth writing system every time. Okay, can I find out LZ system as a function of time? Okay, and then that's the end of the story, because I just plug it in into my law, and my claim is, you trust me, the problem gets solved. So really, the task we have in front of us is how to do this and how to do this. And while I explained to you these two simple steps, I would have covered all the many of the standard tricks that are on display. Okay, so let's get down to this question, which is so I'm going to repeat the question again. Tau z is equal to dlz by dt, and tau z is a scalar equation, so tau z for the system as a function of time equals to what? So this is the first question, and this turns out to be a simple question. We will then tackle this one, but while tackling this one, there's a slight bit of algebra that I might skip, but let me worry about that later. So here is my baton. I'm going to just draw a bigger diagram. Okay, now this is that frozen, my favorite phrase, frozen in time, and we have the magical powers to freeze things in time. Now at that instant of time, frozen in time, maybe there are many external forces on this object which is not a particle, but I can just draw two forces on that particle, and the story is the same for multiple forces. Now this is the situation at that frozen instant of time. The question is clear: what is tau? Okay, so here I'm going to give the answer, and you might find it rather easy to accept the answer. Let me not forget the highlighted point here. I do have a coordinate system and an observer now. There is no end to the number of times I keep talking about this. This is a valid frame of reference. Let's say it's at rest and fixed, and this is the origin. Very important now, because when I say what is tau, that's the first question actually. What is the frame of reference? So I should not never skip that piece of information. Look, there is an origin, there is a coordinate system, and we are solving the problem with respect to the eyes of this observer in this coordinate system. And now the question is valid. What is tau z for this chap sitting here? Well, the answer is this. Things are frozen in time. You got to, this point of application is important, and this is the position vector which I'm going to call as R1. Okay, now the point of application of the force is important, and then the moment I know that badly drawn straight line, I know the position vector at that instant of time for the second force. Now I am ready to give you the answer, and tau z is equal to R1. I'm just leaving out the t, cross f1, okay, and plus R2, and we've spent a lot of time getting through all the ideas of cross product and so on, and we know that this is a vector and this is a vector, and this addition is vector addition. Now in this case it's going to be easy because we're doing only tau z, so they'll just be numbers, but I think you get the idea. The signs are important. Okay, we're almost done, so this is the answer. But here's the key trick. It will be useful to make a slight change in this calculation. I would say a slight modification. Okay, so I think you should choose the red color. You can write and give some prominence to the center of mass by breaking up R1 into two pieces, which I'm just calling it as R center of mass. Obviously at that instant of time, everything is frozen in time, and what is the significance of this vector R1? Okay, right, we'll get back to this in a minute, but what is obvious to you is that RCM plus R1, remember they are vectors, is equal to, okay, R1 dash, sorry, R1 dash, okay, is equal to R1. Now this is obvious from the diagram, and it's crucial. Now I want to just mull for a minute and quickly accept that r1 dash is nothing but the position vector for the observer in our frame of reference moving along with the center of mass. So this part should not be a issue. If you notice that this is the origin, the center of mass is the origin, and r1 dash is a position vector as it appears to the observer who's traveling along with the center of mass. Okay, and therefore you must understand the significance of r1 dash. Now when I do the substitution here, and this is always done, r1 is always replaced by rcm plus, at that instant of time, plus r1 dash, which is nothing but the position vector with respect to the other observer who's traveling along with the center of mass, cross f1 plus rcm. Let's take a deep breath here, because this step is a standard step which will be repeated again and again. Right, so here's where the center of mass enters into the picture. Now I have to get on to the next page, but these are fairly easy expressions to remember, so I'm going to write it down neatly in the next page. Tau z is equal to, at that instant, is equal to rcm plus r1 dash. You must know what r1 dash is. Cross f1 plus rcm is the same rcm that appears in the first term, plus r2 dash. We all know what r2 dash is. Cross f2, and of course these are all vectors. Okay, in the xy plane. Now comes a little bit of algebra, and I'm going to quickly write it like this, and there should not be any problem here for you to accept this. Plus r1 dash cross f1 plus r2 dash cross f2. Right, now comes the final nice interpretation. Now we wanted what tau z is, but it is broken up into two terms which we like. Okay, what are the two terms? The two terms are rcm cross f external on the system, okay, is one part of the torque, plus, now this is the torque at that instant as it appears to the observer who's traveling with the center of mass, right, on an object that is having pure rotation. So we're going to use a notation for this. We'll call it tau about the center of mass z, okay, and this means that this is the torque as it appears to the person who is observing the motion from the center of mass, and this is what he observes is pure rotation. Okay, and for him, if you ask that person what is the torque, what is the torque at that instant, then he will give this expression as the answer. Right, so this formula is very important. Now what we will do is, so I was able to convince you about this. Now I'm not going to be able to convince you about this because it involves some algebra which is not at all difficult, but the first time when a student looks at it, he might get the feeling that it's a little tedious or tough and then get a little unhappy. So the algebra, by the way, is there in Kleppner and Kolenkov. I'll give you the page number very soon, but I'm in a hurry to tell you what is LZ. Okay, so it's very easy to remember. So here's the object frozen in time, and the question is, what is LZ at that instant of time? Remember that these are the axes. Now, what you have to do is first locate the center of mass and tell me at that instant of time what is the velocity of the center of mass. That's the first thing you need to tell me. So let's say I didn't know that. Then the other thing that you need to tell me is what is the pure rotation that you observe from this frame of reference. So there's a guy who's traveling with this frame of reference, and what you ask him what's happening to this object, he will say it's rotating about the center of mass, pure rotation about the center of mass, and it's probably rotating clockwise or anti-clockwise, and it is a pure rotation about this point because this point, according to him, according to this observer, this point is stationary, and that's what qualifies as pure rotation. There is a stationary point and there is rotation, right? So for this stationary object, he sees pure rotation, and therefore he is able to see things like omega at that instant of time, alpha at that instant of time, and of course theta at that instant of time. Now here's the answer. The answer consists of two parts. One, which is calculated as if this whole object is a particle, and you take the velocity of the center of mass. So this is RCM. So RCM cross MVCM plus ICM omega t. Okay, so this I'm now going to give it without a proof, and the only thing I'm going to say is that the proof is very easy. It's just a little bit of algebra, and I'll tell you the page number of, actually I might as well tell you the page number where this algebraic simplification is made. I think it's done on page 261 of this book, and it's not at all difficult, but look how we can interpret these terms so easily, and that's where the happiness lies of the easy way to remember, as well as it looks very nice and simple. This is called the translational component of the angular momentum component and translational part, and this is called the pure rotation part because the formula is exactly like the formula that we derived in pure rotation, and these two when added up tell me LZ. Mind you, and I should have emphasized this at the beginning, we're talking about the same origin and the same position vectors and so on. So there is a fixed coordinate system with the origin and z-axis. So this is very important, and my only worry is that you will not be happy because we haven't done the derivation. So maybe someday you'll do it, but I'm just saying it's a scalar equation because of the nature of the problem we're solving, and it's fairly easy to remember. There is a translational component to the formula, and there is a pure rotation component to the formula. So for example, ICM is fixed, you can get it easily from any handbook, and omega is the omega as it appears to the observer who's traveling along with the center of mass at that instant of time. Right. So let me now summarize the formula. And since I've just done it a few minutes ago, I'm able to remember this so easily. RCM is possible because of the fixed coordinate system. I know the origin, plus tau cm, that is the talk about the center of mass at that instant of time and along the z-axis, and Lz is equal to RCM cross MVCM. Mind you, this is exactly like the angular momentum of a particle, where the particle is of mass m, and plus ICM omega at that instant of time, and so on. Right. So these are, I think I want to remind you that I proved this very easily. This is just the same ideas, by the way, the same ideas, same tricks. The trick is you change the position vector into RCM plus a position vector which is from the eyes of the observer in the moving with the center of mass. So this step is standard, and after that it is just tedious algebra. So now I am in a position to, no, I'm recording. So I'm now in a position to use the law, and the law is tau z at that instant of time is equal to dlz, system, because it's a rigid body, by dt. So the moment I do this, I get the formulas. So let me remind you what the formulas are. The first formula, of course, does not need any justification. Okay, so this is okay. So there's no justification required for this. You already accepted this, and this is going to tell you the position, the translation of the center of mass. What I need to justify is tau cm at that instant of time is equal to ICM alpha as it appears to the observer moving along the center of mass at that instant of time. So I need to justify this. So this will give you your theta t on omega t and so on as a function of time. Now the point I'm trying to make is this is acceptable for you because I'm now going to show in 2 steps that it comes from here. And to use this, I need this. I think I couldn't have done it better than this. This is required. So these 2 formulas are required, and we're going to do problems where I do use these 2 formulas. This, when fed into the law, this is the law. This is, what should I call it? This is definition plus some slight manipulation, which is this, and then is the law. So let us use the law. So this is the grand finale. So let's see if I can write it neatly. Tau z is equal to, writing it a few times really makes you more and more comfortable. And now when I say force external, I'm assuming that you understand that all the forces have been added up vectorially, plus tau z center of mass, and Lz is equal to RCM cross MVCM plus the ICM into omega t. Okay, we all know what omega t is. Now comes the law. Tau z is equal to dlz by dt. Now as I'm going to use the law, I'm going to use another standard trick that comes about quite often in these manipulations. Watch this. I'm going to try. Tau z is already known, so there is no need to. It's already here. Okay, tau z is already here, so there's nothing to do here. Now I'm going to do this small derivative. Okay, watch this. Those of you who still haven't studied derivatives need not worry at all. It's intuitively acceptable. There is a product here, and the way to take I'm taking the derivative, mind you, and the derivative of this chap, m is a constant, is actually ACM, very highly acceptable, plus now the derivative of this chap is VCM cross MVCM, and the derivative of this chap, ICM, is a constant, alpha t. And we're almost there. Here's obvious thing. Now these two, this cross product is 0. This is because this vector is parallel to this vector, and the cross product between two parallel vectors is 0. And here we go. This is equal to force external, says the first law that we've been studying till now. So this is equal to force external, so you have no issues with accepting that this is equal to force external, plus ICM alpha t. Now this is equal to Miss Tau, says who? The law. Okay, and therefore I shall equate it directly to tau z, which happens to be RCM cross F external, and plus tau CMZ, and there you go. You shall cancel this without any hesitation, and we got a grand equation which is valid at every instant of time. And the this is for the pure rotation part. Tau CM at every instant of time is equal to ICM alpha t. Mind you, when you actually go through the steps of the derivation that we have omitted, you will realize that such a beautiful relationship is only possible because of the properties of the center of mass. I leave you to discover that, but I think now you're convinced. And one last time, let's summarize. I have step 1, which is for translation, and step 2, which is for the pure rotation part. And what I mean by pure rotation part in this diagram, in this description, is to tell you what is theta t. For this, I have to tell you what is xcm at a function of time, ycm as a function of time. For this, the equation is F external at that instant of time is equal to total mass into acceleration of the center of mass. And this is something that we are very happy to do. And now I'm saying that we are happy to do this also. Tau z, very easy to calculate. Tau z about the center of mass at that instant of time is equal to ICM. Just look up the tables into, let me just write it differently, d squared theta by dt square, where theta is the orientation change as seen from the observer moving with the center of mass. And the point I'm trying to make is that we have justified this step, justified this for the rigid body. That has been our achievement of this particular lesson, for the rigid body, starting from the rigid body, starting from the law. And the law is this: tau external system is equal to dl by dt. And got to give it to Newton for discovering this definitely not so simple looking law. It's valid at every instant of time. And we did a simpler version of this, which is tau z is equal to dlz by dt, no doubt about that, and therefore we write it as a scalar. And the first part, once again, thanks to Newton, force external on the system at any instant of time, at any instant of time, at any instant of time is equal to dp system by dt at that instant of time. So this solves the translational part, this solves the rotational part, but not without some serious algebra and simplification. But the good news is that the end result is extremely simple. My goodness, that was one long lesson. I hope you guys are still awake, but we will now do problems that will reinforce our use of these formulas, and I'm going to make a list of these problems and send it to you very soon, or I think I should do it right now. I'm sorry. So I'm going to extend this lesson for just that few minutes now. So here is a list of problems that I'm going to discuss in the next video, but I want you to go through it very carefully, because each problem is extremely important. Now page KNK edition 1 and page number 262, problem example number 6.14. Now what I notice is especially in example number 6.15, the author does it by multiple methods. I think this will help you to understand the concepts very nicely. Each example is crucial. For example, 6.16 talks about a drum rolling down a plane, and then this is on page number 264, and this is on page number 265, and then comes a problem which he solves by nearly 3 methods, I think. Then there is another problem, example number 6.17, which is on page number 268. So please read these problems extremely slowly and thoroughly. They contain almost every trick that you need to know and beautifully explained, but unfortunately I will still make a video on this because these examples are so crucial. But I think you will find it nicer if you look at my videos after going through all the problems from K&K, and with that you'll probably be equipped to solve many interesting problems, and of course you will definitely discover a few more tricks during your problem solving, but a majority of them will get covered in this few crucial examples. Alright.